Today we're doing some more Calculus 2 practice problems focusing on arc length. So arc length, we learned it in trig, right? You know that arc length S is equal to R times theta, where R is the radius of a circle and theta is the central angle making a sector that we're we are concerned about finding the arc length of, right? But what if we have a function of x, maybe one like this, and we want to find the arc length between two values, a and b, right? Do we have a formula for that? Yes, we do. And it can be derived using calculus, but we're not going to derive that in this video. We're just going to use it. So the formula is this: s equals the integral from a to b of the square root of 1 plus the function's derivative squared, right? That's all under a square root. So for some function f of x between bounds a and b, its arc length is given by that. And we can also find the surface area if we revolve a function around a horizontal or vertical axis. And it's pretty much the same formula, except we have a 2 pi out front, and we have an radius function, r of x, inside the integral. And we looked at that r of x function a lot in the previous video on shell method. That's just the distance between the function you're revolving and the axis you're revolving around. So it's typically just x, like we looked at in the shell method. So let's look at some examples. These ask us to find the arc length of the function on the given interval. Pretty standard, probably something that would be on your test. So let's look at this. Y equals 2/3 times x squared plus 1 to the 3/2 power. So we know that s is going to be the integral over the interval 0 to 1 of the square root of 1 plus f prime of x. And instead of f prime of x, I'm just going to write it as y prime, because that's how they gave it to us. But y is a function of x, so it's still a dx integral, right? So it's, let's see, 0 to 1, square root of 1 plus, what is y prime? Y is 2/3 x squared plus 1 to the 3/2 power. So y prime is just 3/2 times 2/3, right? The exponent comes down, and we subtract 1 from the exponent. Then, because of the chain rule, we multiply by the derivative of what's inside. The derivative of x squared plus 1 is just 2x, right? So we have a bit of cancellation here, 3/2 and 2/3. But notice, we're concerned not with y prime, but 1 plus y prime squared. So we need y prime squared. Y prime squared is just, we square this and we square this and keep them multiplied to each other. So it's going to become just x squared plus 1 and 4x squared. We also want to add a 1. That's what's going under the square root. So let's try and FOIL this out. We're going to get a 4x to the 4 plus 4x squared plus 1. And using a little bit of algebra, we can rewrite this as 2x squared plus 1 squared, right? Because if you were to FOIL it out, you'd get a 4x to the 4, and you'd get 2x squared, which make a 4x squared, and then you'd get that 1, which comes from the 1 being squared. So we could rewrite this as 1 and 4x to the 4 and 4x squared. And we could rewrite that as 2x squared plus 1 squared. So now we are able to successfully cancel the square root. Now we have the integral from 0 to 1 of 2x squared plus 1 dx, which becomes 2/3 x cubed plus x, evaluated at 1 and 0. Finally, that becomes 2/3 plus 1, or just 5/3. So we probably could have used our calculator to solve this integral from here or even before there, right? But your professor may want you to do it by hand. But if you can use a calculator, use the calculator. But is this integral, is this answer 5/3 reasonable? Well, I'd say so, because isn't this distance right here 1? And we can see that maybe this distance of the curve is a little bit less than 2 based on our scale. But we didn't really need the graph, right? So our answer did end up being accurate, and this is the correct answer, but we really didn't need the graph for it. So if they don't give you the graph, don't feel like you need to graph it out unless they ask you to in the question. But we can find the arc length of this function from 2 to 5 just by finding the integral from 2 to 5 of the square root of 1 plus the derivative squared. So what is the derivative of y? Let's see. y prime. That 5 is going to come down over the 10, and we're going to subtract 1 from the exponent. And this is really the same as 1/6 x to the negative 3. So that negative 3 is going to come down. And we're going to subtract 1 from the exponent again. So 5 over 10 is 1/2. And 3 over 6 is 1/2 x to the negative 4. So we can just plug this in, just like this, into our integral capable calculator. Or we could do a little bit of messy algebra and do it by hand. So I'll do a little bit of it. When we square, we could really factor out that 1/2 first of x to the 4 minus 1 over x to the 4. And we're squaring that. So now we have a 1/2 plus 1/4. We have an x to the 8 minus x to the 4 over x to the 4. That is the outer or the inner, because then this is the other one. So that's outer or inner as well. And we have a last, which is 1 over x to the 8, right? But we're trying to condense this as much as possible, so I want to bring this 1 into there as well. So we could just call 1 the same thing as 4 over 4, right? And then we could factor out the 1/4 out of these, or in other words, just move this 4 into the parentheses and absorb the 1/4. So let's see, this is really x to the 8 minus 2, right? Because this just goes to 1, and this just goes to 1, and 1 minus, or negative 1 minus 1 is negative 2. And we have that 1 over x to the 8. And finally, we're bringing in this 4, right? Can you see that if we were to distribute this 1/4 to that 4, we would just get that 1 over here that we started with. So we did not change the value of the equation. Now, let's combine this 2 and this 4. We're going to get a positive 2 in that case, plus 2 plus 1 over x to the 8. And this could be factored to what we started with, except positive. And you can check that. And now when we throw all of this under a square root, we're able to simplify the square root. So this is really 2 to 5. The square root of 1/4 times x to the 4 plus 1 over x to the 4 squared. So let's see, when we square root this 1/4, we're going to be left with a 1/2. And the square root is going to cancel the square on that function. Now we have 1/2 integral 2 to 5 of x to the 4 plus x to the negative 4, right? And this is now an integral we are capable of solving. So 1/2, integrate x to the 4 and get 1/5 x to the 5th. Integrate x to the negative 4 and get x to the negative 3, with the negative 1/3 out front. Evaluate that at 5 and 2. So I'm going to skip all of that ugly math that you could just plug into your calculator, and we get this number 618,639 over 2,000, right? That would take 10 minutes to do by hand. And we can just approximate that answer to be about 309 units, right? That would be the arc length of this function from 2 to 5. Okay, so now let's look at, those are the, like, arc length really is not that bad, right? You just take the derivative, plug it into the formula, and your professor's not going to throw something crazy on there. They're not testing you on this algebra. They're testing you on the calculus of knowing this formula, right? And being able to do the derivative. So this may have been the first time you've seen derivatives in a while. But what if we were to take some function, this function, and revolve it around the y-axis? It says find the area of the surface formed by revolution over the indicated interval about the y-axis. So can we draw this interval? Let's see. The y-intercept is 1, and it's an x, a 1/4 x squared that's going downwards. So that tells me that at x equals 2, right, if you plug in 2, you get 1 minus 2 squared over 4, which is 0. So it's growing kind of like this in both directions. And we're only concerned about 0 to 2. But we're revolving it that way, right? So this really is going to keep going like that, right? but we're revolving just this shape right here, or that region, around the y-axis. So it's going to come out like that, and then we connect the points. It's kind of like an upside down solid bowl. We call this a paraboloid in Calculus 3. But this is all dense, it's all solid in the middle, and can we find the surface area of it over the interval 0 to 2? Yes, that is just 2 pi times the integral from 0 to 2 of a radius function times that arc length, right? 1 plus c square root of the derivative, let's call it y prime, no, not square root, 1 plus y prime squared. So we need y prime. If y equals 1 minus x squared over 4, then y prime, we can bring the 2 out front and subtract 1 from the exponent. Right, that is the derivative. Okay, then we can square that derivative. Y prime squared is 1/4 x squared, and add 1. So this right here is what's going under the square root. But I'd like to, instead of writing it like that, I want to write it as x squared plus 4 over 4. So this is an equivalent form, right? Because we could just split it into 2 different fractions and get this right here. But I want to do it like this so that when we put it into the square root, and first of all, what is this r of x function? Well, r of x, whenever you revolve around the y-axis, is just x. So we did that a lot with the shell method, and if you have any questions on that, you can watch this video. But basically, the premise is that whatever x value you're at on the function, like here at x equals 1, what is the distance to the axis? Well, we're at x equals 1, and the distance is 1. How about here at x equals 2? What's the distance to this axis? 2. Because we're revolving around that 0, x equals 0, y-axis, the displacement between the function and the axis is just whatever x value it is, hence why we give it x. So we did a lot of work with that in the shell method in the last video, if you have any questions. But then this square root, we already said that y prime squared plus 1 was x squared plus 4 over 4. And we could bring this 1/4 out of the, bring this 1/4 out of the square root as a 1/2, and then we can bring that out of the integral as well. The 1/2 will cancel the 2. Right, so now we have a pi integral from 0 to 2, and we're just left with that square root, or x, and a x squared plus 4. So this is a doable, very doable integral. We did a lot of u substitution in the first 7 or 8 videos of this series, but we can call u the inside composite function always. Du is then 2x. So what does that mean? That means we want a 2 next to the x, so we have to put a 1/2 out front to account for it. We could bring that 2 out here and cancel the 1/2, so we really didn't change the value of the equation, right? So now we have a pi over 2, 0 to 2 of u to the 1/2 du. We can definitely do this integral. So pi over 2, we're going to add 1 to the exponent. U becomes 3/2, and then we divide by that new number, or in this case, multiply by the reciprocal. Instead of plugging back in that function of u, I'm just going to change the bounds. So these right here, technically all of this is incorrect because I have x bounds on a u function. So let's change that bound. It's not 0. It's u of 0, right? U of 0 is just 0 squared plus 4, or 4. And this is really not 2. Let's plug in 2 in there, u of 2, and we're going to get 8, right? Because 2 squared plus 4 is 8. So by doing that, we do not have to plug back in that function of u. We can just change the bounds. So we have pi over 2. And let's take out that 2/3, right? We can see that this 2 cancels that 2, and we're just left with a pi out over 3 out front. Then we have 8 to the 3/2 minus 4 to the 3/2. Well, 4 to the 3/2 is easy, right? Because you square root 4 and you get 2, and then you cube 2 and you get 8. but I don't believe that 8 to the 3 halves is that much easier. 8 to the 3 halves is, well, let's see. What is the square root of 8? It's 2 square roots of 2. And then we're cubing that entire thing. So we're going to get in 8. Oh, it doesn't really work, right? We're going to get an 8 and a square root of 8. But then that just can become a 16 square root of 2. So it's not pretty. Here's my point. This just becomes a 16 root 2. We can plug all of this into the calculator and approximate it to be about 15.3. So that is the surface area that we get from this equation, right? Or revolving this function around the y-axis. The surface area of this paraboloid is 15.3 units. We're not really too concerned about the units in calculus. Anyways, let's move on to this function. I guess we will have to graph it from 1 to 8. So let's see. It has a y-intercept of 2. What happens when you plug in 1 into this function? I'm just going to plug in 1 and 8 to see. That'll probably tell me what I need to know about what this function is doing. When we plug in 1, let's see, y of 1, we're going to get 1 to the 1/3 plus 2. That's just 1 plus 2, or 3. And we can also plug in 8 into the function. We're going to get 8 to the 1/3 plus 2. And that is equal to, let's see, 8 to the 1/3 is just 2, right? Because 2 cubed is 8. And 2 plus 2 is 4. So at 1, we have a y value of 3. At 0, we have a y value of 2. And at 8, 2, 3, 4, 5, 6, 7, 8, we have a y value of 4. So you can kind of see how this thing grows, almost like a square root function, except a little bit flatter. It's going to keep going. It's not perfect, but it'll do. We're going to revolve it around the y-axis, which means it's going to make something like that. And we're also going to include all of this area under it. And then we connect the points. This point comes to here. This point comes to here. This point comes to here. And this point comes to here. So it's kind of like, you know, I don't know, a cylinder, and then it tapers off towards the middle of that cylinder. But what is the surface area of the shape, right? Well, we're able to do 2 pi times the integral from 1 to 8 of the, since we're revolving around the y-axis again, that r of x function is just x, and the square root of 1 plus the derivative squared. What's the derivative? Y prime. The 1/3 comes out front, you subtract 1 from the exponent, and you square that to get a 1/9 x to the negative 4/3. So I'm not going to bother doing all of the algebra in that case, but it's just going to approximate to about 199.5. You can do all the algebra if you'd like, but I don't see how, I don't think it's worth it in this case. So that is how you find the surface area revolving a function around an axis. Remember, we get that formula for finding the arc length of a function between two bounds. So that's how you do arc length and surface area. And I also just wanted to point out, and it really doesn't matter because, like I said, you don't need the pictures to do this, but really, I'm thinking about it, and when you revolve around this y-axis, this part is really not brought with it, right? It's not like, you know, finding volumes. When we revolve it around the y-axis, we're just left with that kind of shape that's left, right? We're not really concerned about any of this. Do not want anyone to get confused. Oh, that was like a kind of hypothetical. What would happen to the side walls if this were to become a 3D shape, but it's not? It's kind of like this, you know, if you looked at it from the side view, it's kind of like that, right? So that is what we just found the surface area from, not the cylinder. So I just wanted to clear that up. But yeah, that is how you do arc length and